Today we're going to talk about elementary matrix operations and elementary matrices. First, let's review some discussions last time on change of coordinates. Recall that if we have a triple consisting of linear transformations from a vector space V to a vector space W, we can define a vector space as follows. By vector addition will mean we can take two linear transformations, T1 and T2, and define a new linear transformation, T1 plus T2, as that map that takes the vector x to the sum of vectors T1 of x plus T2 of x. We can also define scalar multiplication as follows. Given a linear transformation T1 and a scalar c, we define c times T1 as that linear transformation that takes a vector x to the vector c times T1 of x. With this, we're able to prove that given a vector space V that is n-dimensional, a vector space W that is m-dimensional, then V is isomorphic to the collection of n tuples, that is V is isomorphic to f to the n, W is isomorphic to f to the m, and LVW is isomorphic to the collection of m by n matrices. We also see that if T is an isomorphism, then the matrix representation of the inverse of T is just the inverse of the matrix for the representation for T. The upshot of this theorem is that we can replace any finite dimensional vector space V with the collection of n tuples. That is, instead of thinking of V as an abstract entity, we can make it very concrete by thinking of V as f to the n. We have the following theorem that explains how to relate two different bases, let's call them beta and beta prime. Let's denote a matrix Q as what we find, that is the matrix representation of the identity map as we go from the basis beta prime to the basis beta. The jth column of this matrix Q is just the coordinate vector with respect to beta of the jth vector xj prime from the new basis beta prime. This matrix Q is invertible, and its inverse is the n by n matrix that we find by considering the matrix representation of the identity map going from beta to beta prime. Next, the standard representations with respect to beta and beta prime are related by this matrix Q. And finally, for any linear transformation T going from a vector space V to itself, then we can find n by n matrices A, B, and Q, which make the following diagram make sense. In other words, let's think of A as the matrix representation with respect to the basis beta, and we'll think of B as the matrix representation with respect to the new basis beta prime. Then B and A are related by the expression B equals Q inverse times A times Q. Recall that our map phi sub beta that takes a vector x to its coordinate vector with respect to the basis beta is called the standard representation. The invertible n by n matrix Q is called the change of coordinates matrix. Observe that if we were to choose beta to be the standard basis, then we can write all of the columns of our matrix Q by simply placing in the vectors in the new basis beta prime. If A and B are two n by n matrices, we'll say that B is similar to A if there exists an invertible n by n matrix Q such that B equals Q inverse AQ. Before we go any further, let's discuss some motivating examples. I'd like to focus on the following matrices. Here's a matrix with 2 rows and 4 columns. This is a 2 by 4 matrix. And here are the 4 matrices that form the standard basis for the collection of 2 by 2 matrices. We can express the following matrix products by multiplying the 4 different matrices on the right times this matrix here, A, that you see at your upper left. Here's one way to think of the expressions that we found. For E11 times A, the idea is that we're taking row 1 of A and placing it in the first row here. In other words, in the first row, we're going to place the first row of A. For E12 times A, in the first row, we'll place the second row of A. For A21 times A, in row 2, we'll place row 1 of A. And finally, for E22 times A, in the second row, we'll place in the second row of A. Using this, we can write down a few more identities. Let's take a look at this matrix 1, 0, 0, 1 times A. This matrix, of course, is the identity matrix. The entry 1 here in the upper left, we can identify that with the matrix E11. Notice that E11 times A gives us back the first row that you see in red here. For the identity matrix, the lower right-hand entry corresponds to the matrix E22. Notice that this product will give us back the second row that you see here. We have a similar expression now for the matrix 0, 1, 1, 0 times A. The 1 in the upper right we can express as E12, and the 1 you see in the lower left we can express as E21. Let's consider this matrix here, 1, 0, 0, C, where C is any scalar. The entry in the upper left corresponds to E11, and the entry in the lower right corresponds to a scalar times E22. Finally, let's consider this matrix 1, 0, C1, where again C is a scalar. The upper left corresponds to E11, the lower right corresponds to E22, but now the lower left corresponds to a scalar times E21. Staring at these four examples, we now see that if we multiply our matrices on the left, then either we're interchanging two rows, multiplying one row by a scalar, or adding a multiple of one row to another. We're going to try to explain what happens here in a more general sense. This will lead us into elementary matrix operations. Say that we have an m by n matrix. That is an array with m rows and n columns. Remember that rows move left to right and columns move top to bottom. There are three types of operations that we can perform on these rows. First are type 1. We can interchange any two rows. Second is type 2. We can multiply any row by a non-zero scalar. Third is type 3. We can add a scalar multiple of any row to another row. I should point out that you can also do all of these for columns as well. These are called the elementary row operations, or if you will, the elementary column operations upon changing the correct words. An elementary matrix is any n by n squared matrix E that is obtained by performing exactly one of these three elementary operations on the n by n identity matrix. It doesn't matter here whether you're allowing an operation on the rows or the columns. Let's let A be an m by n matrix, and suppose that B is obtained from A by performing an elementary operation. There are three cases we need to consider. If this were a row operation, then B is simply E times A for some elementary m by m matrix E. Conversely, if E is an elementary m by n matrix, then E times A is that matrix obtained from A by performing the exact same elementary row operation that produces E from the m by m identity matrix. If this were a column operation, on the other hand, B is A times E for some elementary n by n matrix E. Conversely, if E were an elementary n by n matrix A, then A times E is that matrix obtained from A by performing the same elementary column operation which produces E from the n by n identity matrix. Finally, elementary matrices are invertible. The inverse of an elementary matrix is of the same type. We'd like to prove these theorems, but first let's begin with an observation. Let EPQ denote that square matrix whose only non-zero entry is in the pth row and qth column. We can try to multiply EPQ on the left times A, or EPQ on the right times A. Here, we're looking at the ij entry of the matrix EPQ times A, or the ij entry of A times EPQ. Instead of looking at these formulas, we can think of this a bit more intuitively. EPQ times A is that n by n matrix where in row P we'll place in row Q of A. All of the other rows of this matrix will be 0. On the other hand, if we were to consider A times EPQ, this is that n by n matrix whose in column Q we place in column P of A, and all of the other columns are 0. In particular, we can write A as the following. Here, when we write EII times A, all that we're doing is we're looking at the various rows of A and placing them in one at a time. Similarly, when we have A times EJJ, we're looking at all of the various columns of A and placing them together one at a time. Now, in order to prove the theorem, we're going to divide our proof into 3 types of elementary operations. First, let's look at type 1, where we interchange either rows or columns. Let's say that B is obtained from A by interchanging 2 rows, P and Q. The idea is that if we take a look at the expression from above for A, we're going to replace EPP times A, namely row P, with EPQ times A. Again, in row P, we'll substitute and replace row Q of A. Similarly, instead of writing EQQ of A, we'll replace that with EQP of A. The idea is that in row Q, we'll substitute and replace in row P. Now, summing in a very similar way that we found up above, we find this matrix E that you see at the right of your screen. Notice that E is that m by m matrix obtained from the identity matrix by interchanging rows P and Q. The idea now is that if we interchange the 2 rows again, then we have the original matrix. This means that in order to undo a swapping of 2 rows, we just swap 2 rows again. This is the same as saying that the inverse of our elementary matrix E is just E. A similar argument explains what happens if you interchange 2 columns. All that we're doing is multiplying on the right instead. Let's consider operations of type 2. That is, we're going to multiply either a row or a column by a non-zero scalar. Let's say that B is obtained from A by multiplying row P by a non-zero scalar C. Here, we can write B as the sum that you see on your screen, but notice that instead of having just the pth row, EPP times A, we'll have to replace that with C times the pth row, namely C times EPP times A. Again, factoring, we can write our elementary matrix E as above. Here, we see that E is that m by m matrix obtained from the identity matrix by multiplying the pth row by a non-zero scalar C. If we multiply the pth row by the reciprocal of C, then we've simply undone multiplication by the scalar. So this means that we can also express the inverse of our matrix as an elementary matrix. A similar argument explains what happens if you replace row by columns by multiplying on the right instead. Finally, let's discuss type 3. these will be adding one multiple of a row to another. Let's say that B is obtained from A by adding a scalar multiple of row Q to another row P. Here, we're going to replace row P with a scalar multiple of row Q. So we're going to simply add C times EPQ times A. Factoring, we then see this elementary matrix E. Here, E is that M by M matrix found by adding a scalar multiple of row Q to row P. To undo this, we simply need to subtract a scalar multiple of the same row. So we see that E inverse is indeed in this similar form. A similar argument works if we replace rows with columns, but now we multiply on the right. Thanks for watching.